Okay, well, my name is Anil Kulkarni. I am at Pennsylvania State University, Mechanical Engineering. I've been a professor there for more than 35 years. Just to give you a little bit background, I graduated from IIT Bombay with 2 BTechs and did my PhD at Brown University, and then since then I'm at Penn State. So I'm going to talk about mathematical modeling of a certain manufacturing technique called electron beam physical vapor deposition. And the reason I chose to talk about this, I mean I kind of have a workshop about this, was because number one, it's a very we just finished this work earlier this month. In fact, first week of this month, my student Kevin, he actually put together a presentation, many slides, but that is the project that we had. It has been going on for a while. Takes good 5 or 6 years of full-time work. And the way typically it works is that we have a research project, we come up with a certain title and thesis, thesis project scope, and then the student comes and joins and does the project. So 2 of us were working on that. I'm from mechanical engineering side and Dr. Singh is from materials side. This is a interdisciplinary project between mechanical engineering and material science. And so I wanted to show you how this interdisciplinary projects work. And the other thing I wanted to show you is that how we can take a practical problem and it can become very fundamental research problem. It can get very involved mathematical problem. So modeling of electron beam physical vapor deposition. So I'm going to talk about coating. Okay, there is coating in many places that we see. Do you know of any examples of coating? Any type of coating. Why do we do coating and where is it? Paint, that's a good example. Exactly, investment casting. Electroplating, that's very, including, your 1 gram gold jewelry and all that, there's this coating there. And coating is very important. So painting, what you just said, it's there. And what it involves is basically we have a substrate of whatever shape, or you can think of as a car handle or something. It looks nice and shiny, but inside that it is not that. It basically is a coating that is showing. And there are different types of coats that you put on there for different purposes. Usually it is to protect the part, but also so that it becomes stronger or it looks prettier, or all those different things. So these are very typical examples. But when you go in engineering, there can be very advanced level. Well, this is a coating process. This is how it is done often. These are just a couple of the different processes. You can actually spray the material on the part, whether it is small part or a very gigantic part like this. You can spray it on there and for various different purposes. But there can be very high-tech applications of coating. And to mention one, if you're looking at hypersonic vehicles, hypersonic means they're at very high speed. The speed is many times the speed of sound that the vehicles go in. And when a hypersonic vehicle enters the Earth's atmosphere, or when it leaves the Earth's atmosphere, because of the friction, there is a very large amount of heat that is generated by friction on the surface. It is shown in red here. And that type of heat generated, which causes high temperature, there are not too many materials out there which can easily withstand that. So they try many different ways of doing that. In fact, they've tried sacrificial tiles. So the coating itself, they purposely let it burn and go away so that inside of the vehicle is not affected. Okay, and so this is very high, advanced level thing. So one of the problems with that is that first of all, the surface is made of some kind of a refractory material. Refractory material is something that withstands high temperature. A typical refractory material is a ceramic, let's say. So if outside is ceramic or titanium, like high temperature material, you want to still try to cool it down. You want to take away the heat as the heat is generated. So you want to put in their cooling channels, small micro cooling channels. I'm talking about a millimeter or smaller diameter cooling channels, and you circulate in the cooling channels some kind of a very cold fluid. Often it is as cold as some kind of a liquid hydrogen or oxygen, that is circulated through, and it is kept cold. One problem we were looking at was, let us say this is the edge, front edge of the vehicle. This is going in supersonic speed in atmosphere. So because of air friction, there's very large amount of heat that is generated there. Now outside is ceramic, some sort of ceramic. These are the tubes. The tubes don't have to be circular, they can be any shape. So this is the tube. Inside the tube we send some kind of a cryogenic liquid. Now the problem is, and there are multiple problems, at very high temperature ceramic will start, let's say we make a tube of some material, some rhenium, titanium, whatever metal. The ceramic starts dissolving literally into the tube. At the same time, the inside fluid starts corroding the tube surface. So typically what you want is something that will keep the dissolving of ceramic away. It is called diffusion barrier layer, DBL. So the diffusion of ceramic or any material should be stopped. On the other hand, inside you want it to be resistant to corrosion for whatever. I mean, for the Mars mission they were talking about lithium fluid, and these are very extremely advanced kind of type of applications. This is Mars mission. When they're going to send somebody to Mars, it is going to take several months to go there and several months to come back, and you should have something going on all the time. And so and of course there are different problems. The space temperature is very low. It is 2 degrees Kelvin. The inside temperature is 300 degrees Kelvin. So it's a reverse problem. In any case, you need something that is protected in terms of heat and corrosion and diffusion and all these problems. And for that, what you need is a tube of certain material, but you need different types of layers on that, because one material is good for corrosion inside, the other one is good for diffusion of something, the other layer is good for heat resistance, and so on. So there are different layers of tubes, and that is done by coating. Problem with coating is that if you look at the coating, now this one probably has some kind of a laminate on the top, right? This table, it's a coating. But when you look at this type of application where the temperature goes up and down, you can imagine it will change the shape slightly and the coating will flake out. It will get released because of the stresses when it goes, when it expands and contracts. So how do you take care of that problem? So let's say you want to make a tube with all the coating in such a way that the coating doesn't come loose. Well, one way to do that is you don't have an actual layer of something, but you have a layer which is already diffused inside. One way to do this is, let's say I have two tubes of 2 layers. So this is what actually we were doing. So this is a molybdenum material, and there is a diffusion barrier layer, the different material A, material B, and we want to create a bond between the two. If you make a simple bond, when it expands and contracts, it will fall apart. So one way to do that is, in here you actually purposely diffuse the material continuously, so that the concentration of, say, this goes from 100% to 0% at this point, concentration of this goes from 100% to 0% at this point, and it is kind of slowly diffused into each other. So there is no single interface. Right? It's kind of a diffused interface. And yesterday for lunch, I was looking at it. There was dhokla, right? And there was this white dhokla there with nice green line in between. But this green line kind of faded on both sides. It is a continuously diffused, nice bonding. So you couldn't separate it clear. So, but this you want to make dhokla like this, but that will withstand very high temperature. This is the type of coating you want to make, and then you want to make multiple layers of this. And typically, this is material 1, material 2, material 3, material 4. Each one is diffused into each other. Now, how do you do that? And these are typically very high temperature materials. I mean, steel and all that will not withstand there at all. These are, you're talking about 3000 degrees, 2000 degree, 3000 degrees C, which is very high temperature. Pretty much no other material here will withstand that. And this is the actual problem. This is the ceramic layer, and so to stop from, this is the cooling tube, and you have different materials which are diffusing into each other, and you make a coating out of it. So one way to do this is what is called physical vapor deposition. What you do in here is you have something called you have a target, which target means the material that you want to coat it with. So if this is the object and I want to coat this with some other material, then I take a rod of that material. Say this is titanium material and this is molybdenum, this is different. So I, using an electron gun and magnets, you heat this so much to thousands of degrees, it melts, it boils, it evaporates, and a vapor goes out, and a vapor deposits on the surface. So this is kept here, this is the target, and you vaporize it, and it goes on there. And in reality, actually, this is what a typical electron beam physical vapor deposition process looks like. This is the electron gun, and there's a rod, and it evaporates the material, and it goes, it's a vacuum chamber, and it deposits on something there, and it goes there. That's the way typically it is done. Now, if you want to go a little more advanced, this is the facility in our university, Penn State, Pennsylvania State University, and it looks, well, from outside it looks like this. This is a chair, so you can get some idea of what size it is. It's about 1 meter by 1 meter, you can say. Okay, chamber. The chamber looks like this. At the bottom there are 3 rods, each of about 50 millimeter diameter, and they're made of different materials that you want to do coating from. And imagine there is a part here. So let's say you make a tube here. Actually what we do is, what we have done is, we took a very thin carbon lead, that like pencil lead type of rod. So literally you take it from the pencil inside rod here. Then you start evaporating A by putting electron gun there, and this is very high power. Each electron gun here is 45 kilowatt. So you can imagine it's a huge amount of power, and you melt it, you evaporate it, and in this little carbon pencil lead, this is spinning and keeps on evaporating on that one. So it makes a layer of A, and then after a while you slightly start slowing down A evaporation, but simultaneously start B evaporation. So B starts evaporating, A is also evaporating, so mixed material is going there, but A is slowly shut down and B is slowly brought up, so that A and B get mixed in together, and a layer of B starts developing on the tube. So if this is a tube, then this is the pencil lead here. First A goes on there, then A goes on slowing down, but B comes in, and then B starts growing, and then you stop B, and then you start C. Again, same way, it is a diffusion layer, it is not a distinct layer. So you don't really I mean, there's no question of this coming apart because it's not a simple layer. The idea is when you're done with that, we take the tube and we bake it at a very high temperature so that the carbon inside gets evaporated and goes out. So what remains is a nice tube with A inside, then B on top of it, and then C on top of it. And we can choose whatever materials that we want, all kinds of molybdenum, rhenium, titanium, or even hafnium carbide, whatever. So that is a basic process. And so this is the chamber, and it kind of goes on for several hours, or for a day even, and it builds up a tube from there, and it can be used in space applications or whatever. So this is a schematic of the same diagram. Those are the A, B, C rods there. This is where the substrate is, and you can go on spinning if you want even distribution of coating on there. These are electron guns. That's how it works. We want to now mathematically model the process. Then how does it work, or this coating? Imagine I have a surface like this, kind of a long surface, maybe like this. At the bottom, I evaporate, and this evaporated stuff is depositing on the surface. What you can expect is that exactly above the rod, there'll be maximum deposition. If this is a surface, this is a plate like this, and as you go away, there'll be less and less and less, right, at the further end. So if you take a cross section of the plate after you deposit it, the actual deposit will look like this. It will be thick in the middle, then thinner, 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 and it will go to zero. You go to zero on both sides. And you want to know how will be the distribution exactly. And the reason you want to know is that, first of all, each run takes place for many hours, maybe a day. It is very expensive to set up the whole project. So each tube that we make on that one, about a 6-inch long tube, it can cost a few $1,000s. Okay. So I mean, it is a nice process. But if you can predict how it will be distributed, how much it is, how much is A, how much is B, it will be much nicer, because then you can first you can run the model and find out if it's working fine, and then you set it up, and then you put everything together. Okay. So how do you do the mathematical model there? So for